Good morning. Welcome back to our physics class. Today, our topic of discussion is bending moment. In the last class, we had seen what is a bending moment. Today, in this class, we are going to find out an expression for the bending moment. For that, we are considering a beam, as you can see in the first picture, and we are considering only a small portion of the beam bounded by two transverse sections AB and CD. That means we are just considering a small portion of the beam included by AB and CD. Now we are going to see what happens to the beam after bending. So the upper picture shows you the picture of a beam before bending, and the lower picture gives you the changes occurred in the beam after bending. So after bending, AC becomes A dash C dash. That is, AC is elongated to A dash C dash. Now what about BD? BD is compressed or shortened to B dash D dash. And you know that there is a surface or layer in which neither elongation nor compression occurs. That surface is known as neutral surface. Here EF represents the neutral surface. And EF is neither elongated nor shortened. So the small portion of that beam is bent in the form of a arc, in the form of a circular arc. So this arc is having an angle theta at the center of the curvature. So arc subtends an angle theta at the center of curvature. So we can see after bending, we can see a portion called arc. If we complete that arc, we will get a circle, isn't it? So that circle is having a particular radius. So that R is we consider R as the radius of curvature. Radius of curvature of neutral surface, that is E dash F dash. We know that EF is the neutral surface, and after bending EF is neither elongated nor shortened, but we are renaming it as E dash F dash, so that E dash F dash is equal to EF itself. So R represents the radius of curvature of neutral surface E dash F dash. We are considering a filament or a layer, a longitudinal layer at a distance Z from the neutral surface EF in the unbent position. So GH is a filament at a distance Z from the neutral surface EF, and now this GH has become G dash H dash after bending. And we had already said that EF is the neutral surface which is neither elongated nor shortened, so that E dash F dash is equivalent to EF. Now how will we find the value of EF or E dash F dash? We have the relation angle is equal to arc by radius. So here angle is theta, so theta is equal to arc. Arc is E dash F dash by radius. Radius is r. So theta is equal to E dash F dash by r. So E dash F dash is equal to r into theta, and we know that E dash F dash is EF itself. So E dash F dash is equal to EF, which is equal to r theta. But from the first figure you can see that EF is equal to GH before bending, isn't it? So you can write GH is equal to EF, which is equal to r theta. Now GH has elongated to G dash H dash. Now what is the value of G dash H dash? Again we can find it out from the relation angle is equal to arc by radius. So arc is equal to angle into radius. So angle is theta. Now what is the radius to the filament G dash H dash? Radius to the filament EF is r, and the distance from EF to GH is z. So the radius of the filament GH is r plus z. So G dash H dash is equal to r plus z into theta. So we have got GH as r theta and G dash H dash as r plus z into theta. So GH has elongated to G dash H dash after bending. So we can find out the increase in the length of the filament. How? By simply subtracting, isn't it? So G dash H dash minus GH will give you the increase in the length of the filament. So simplifying r plus z into theta minus r theta as cancelling r, we will get it as z theta. So that is the increase in the length of the filament. Which filament? GH. So after bending, GH has been elongated to G dash H dash. So we had found out the increase in length of the filament as z into theta. So we got the increase in length, isn't it? Now we can find out longitudinal strain. So longitudinal strain is equal to change in length by original length. So we had calculated the change in length as z theta. And what is the original length? Original length of GH is EF itself, that is r theta. So z theta divided by r theta, which will give you z by r. So let that have equation be with you. Now we are going to the second section of derivation, that is, for that we are considering a section of a beam perpendicular both to its length and plane of bending. That means we are taking the cross section of the beam. And we consider the cross section as P, Q, R and S. PQ being the breadth of the beam B, QR being the thickness of the beam, that is D, and MN. So we are taking the cross section. So here you can see a rectangular portion in which the central line will be the neutral surface. So MN lies on the neutral surface. The forces acting on the filaments in the portion MNSR, that means the lower portion of the neutral surface, will undergo contraction, and the forces acting on the filaments in the portion PQMN undergo elongation. Once again, we are taking a cross section of the beam, that is PQRS, so that the PQ is the breadth of the beam and QR is the thickness D of the beam. and MN is the central line that lies on the neutral surface, which is neither elongated nor compressed, and the upper portion of MN is elongated and the lower portion is contracted. So the forces acting on the filaments in the upper portion produces elongation, whereas the forces acting on the filaments in the lower portion will produce contraction. That means one force produces elongation and other force produces compression or contraction. That means the forces acting on the filament in the upper and lower portions are opposite to each other. And we are taking a point A, which is at a distance Z from the neutral surface. You can see it in the picture. We are considering a point capital A, which is at a distance Z from the neutral surface. And we are considering a small area around that point A, and that small area is represented by delta A. So we are considering a small area delta A at the point capital A at a distance Z from the neutral surface. And we had already calculated the expression for strain, isn't it? The strain of the filaments passing through this area. The strain is Z by R. So how can we calculate Young's modulus? We know that Young's modulus is equal to stress by strain. So we are going to calculate the stress at the point A. So stress is obtained from the above equation as Young's modulus into strain. And we have Young's modulus of the material as Y itself, and the strain we calculated it as a Z by R. So the stress at the point capital A is Y into Z divided by capital R. So we got stress. Now what is the force acting on the filaments passing through this small area delta A? We know that stress is equal to force by area. So force is equal to stress into area. So stress we had calculated it as YZ by R, and the area we had considered it as a delta A. That is a small area at the point capital A, that is a delta A. So we had calculated the force acting on the filaments in the given area delta A as YZ by R into delta A. Now what is the moment of this force? So moment of this force about the line MN is moment. How we will calculate moment? As force into distance, isn't it? Force into perpendicular distance. So we had calculated force as YZ by R into delta A into the distance to the considered point A, and it is Z from the line MN. So moment of the force about the line MN is equal to YZ by R into delta A into Z. So multiplying and rearranging, we have Y into delta A into Z square by R as the moment of the force about the line MN. So this is the moment of the force acting on both the upper as well as lower portions, and this moment of the force are in the same direction. We had already said that the forces are opposite, isn't it? Because the forces produces elongation to the upper area and contraction to the lower area. That means the forces are opposite to each other. But here the moment of the forces acting on both the upper and lower portions are in the same direction. And we had already considered an area PQRS, a segment or a portion PQRS. and we can divide it into small elementary areas. So we had already considered a small area delta A, isn't it? So we can consider the entire area PQRS as small elementary areas. And we can calculate the moment of forces acting on the filaments passing through the area. So how we will get the total moment? Adding all these moments, we will get the total moment, which is equal to the bending moment. See, we had derived the moment of the force about the line MN with the considered area delta A only. So now we are considering this moment of this force for the entire cross section of the beam PQR. So what we have to do? We have to add all the moments together. So we will get the total moment, that is equal to the bending moment. So addition in mathematics is denoted by sigma. So the forces acting on the both upper and lower portions are opposite, but the moments of the forces are acting in the same direction. So we can find out the bending moment as adding all the moments together. So we can put a sigma sign to show the summation. So sigma of y into delta A z square by r. Now y is the Young's modulus of the material, isn't it? It's a constant. We can take it outside. So y into sigma delta A into z square. See, A and Z are the delta A and Z are the varying quantities. So sigma can be given to only that quantities. That is sigma of delta A into Z square. So here initially we had considered a small area delta A at the point capital A, which is at a distance Z. If you are considering another point, we can also consider a small area there, which is at a distance, at a particular distance. So delta A and Z are changing. So sigma must be given for delta A and Z. So y into sigma of delta A z square divided by r. You know that a radius of curvature will be a constant, isn't it? So the expression for the bending moment is y into sigma delta A z square divided by r. And this sigma into delta A into z square is known as geometrical moment of inertia of the sectional area, and it's also known as second moment of inertia, denoted by I suffix g. So Ig represents we know that capital I is used to represent moment of inertia, isn't it? So I suffix g represents the geometrical moment of inertia of the sectional area. So we can write bending moment as y into Ig by r. So the expression for bending moment is y into Ig divided by r, in which y into Ig is known as flexural rigidity. So in this class, we had derived the expression for the bending moment. For that, we had considered a beam in which the upper layers undergo elongation and the lower layers undergo contraction after bending. And we had initially we found out the expression for strain. From that we calculated stress. From that we got the expression for force. Then force into perpendicular distance will give you the bending moment. For that we had initially considered a small area delta A. So considering the whole beam, we have to integrate or take summation. So here we are taking summation. So sigma is given, and so y into sigma delta a z square by r is the expression for bending moment, where sigma delta a into z square is known as the geometrical moment of inertia and y into ig is known as flexural rigidity. So we have got the expression for bending moment. Now we can calculate the bending moment for rectangular cross section as well as a cylindrical cross section beam. For that, let's have a look on the moment of inertia of the body. We know that moment of inertia I is represented as mr square, isn't it? So in terms of summation, you can write it as sigma I mi ri square, which is equal to m into k square, or you had studied it as mr square, where r is or k is the radius of gyration. And we had already seen what is geometrical moment of inertia, that is Ig, which is equal to sigma into delta A into z square. And we know that z is the distance of the area delta A from the axis. So we can substitute sigma into delta A as, that is a summation of summation of area, isn't it? So it is given as capital A itself, and z square is given as k square, where k is the radius of gyration. So Ig can be written as A into k square. So with this, we can calculate the moment of inertia of a rod of rectangular cross section with breadth B and thickness D. So here we are considering a rod of rectangular cross section with a breadth B and thickness D. So what will be the area? Area is equal to breadth into thickness, so B into D, and radius of gyration for a rectangular cross section is given as K is equal to D by root 12. From that you can calculate Ig, that is the geometrical moment of inertia, as BD cube by 12. So what will be the bending moment? You can substitute Ig in the expression for bending moment and can find out the expression as y into BD cube by 12r. You just substitute it in the expression for bending moment and you will get the expression as y into BD cube by 12r. Now, for a cylindrical rod of radius r, the rod is cylindrical. So what is the area? Radius is r, means area is pi r square, and radius of gyration k is equal to r by 2. So what is Ig? That is the geometrical moment of inertia. Ig is equal to A into k square. Simplify and you will get a pi r raised to 4 by 4. And you can again calculate the bending moment by yourself. So bending moment is equal to y Ig by r. So that is y into pi r raised to 4 by 4r. Do it by yourself for rectangular cross section as well as for cylindrical rod. Calculate the value of bending moment. Okay, so I think the class is clear to you. In this class we had seen how to get the value of bending moment, how to derive the expression for the bending moment, and also found out the values of bending moment for rectangular cross sectional rod as well as a cylindrical rod. Thank you.